So you want to know about a white hole. It's one of those ideas in physics that sounds like science fiction. And maybe it is, but it comes from a very real place. It comes from the same math that gave us black holes. To understand a white hole, you have to start with a black hole. They are two sides of the same coin. A black hole is a place in space where gravity is so strong that nothing can escape. Not even light, it's like a one-way door. You can check in, but you can't check out. This idea came from Albert Einstein and his theory of general relativity. He said that gravity isn't a force pulling things together. Instead, it's a bending or warping of space and time. Imagine a heavy bowling ball on a trampoline. It creates a dip. If you roll a marble nearby, it falls into that dip. That's gravity. Now, imagine something incredibly heavy, something way heavier than a star. It would create a dip so deep that it becomes a bottomless pit. That's a black hole. The edge of this pit is called the event horizon. Once you cross that line, there's no turning back. All paths lead to the center. The center is a point called a singularity, where all the matter is crushed into an infinitely dense point. Physicists worked with Einstein's equations for years. They confirmed that black holes should be real. And then we found them. We've seen stars orbiting nothing. We've seen matter getting ripped apart as it falls into them. We've even taken a picture of a black hole shadow. They are a real part of our universe. But here's where it gets strange. When scientists looked very closely at the math that describes a black hole, they found something odd. The equations are symmetrical. They work just as well forward in time as they do backward in time. Think of a video of a ball falling to the ground. You can play it forward and it makes sense. Gravity pulls it down, but you can also play it in reverse. The ball would leap off the ground and fly into your hand. The laws of motion don't forbid this, even though we never see it happen in real life. The math for a black hole has a similar feature. The black hole solution describes matter falling in and getting crushed. The time-reverse solution describes something else. It describes matter erupting out of a singularity, flying away from an event horizon that nothing can cross from the outside. That's a white hole. It is the exact opposite of a black hole. A black hole is a region of space-time you can only enter. A white hole is a region of space-time you can only exit. A black hole is a cosmic sink. A white hole is a cosmic fountain. Nothing can get into a white hole. If you were in a spaceship and you tried to fly into one, you would never reach the event horizon. It's like trying to run up a downward escalator that's moving infinitely fast. You can try all you want, but you will never get to the top. Time and space itself are flowing outward from the center so fast that nothing can move against that current. Instead, things can only come out. A white hole would be a place where matter and energy spontaneously burst into the universe. It would be a source, a beginning point. This idea comes from something called the maximally extended Schwarzschild solution. That's a fancy name for the most complete version of the math that describes a simple, non-spinning black hole. This mathematical map of space-time doesn't just have a black hole and our universe. It has more. It has a black hole, a white hole, and two separate universes connected by a bridge. This bridge is what we often call a wormhole, or an Einstein-Rosen bridge. According to this pure mathematical picture, if you fell into the black hole in one universe, you would travel through the wormhole and come out of the white hole in the other universe. It sounds like a perfect cosmic transportation system, but there is a very big catch. This is where the math stops looking like reality. The first major problem is formation. We know how black holes form. A giant star, many times bigger than our sun, runs out of fuel. Its own gravity becomes too strong for it to support itself. The star collapses inward. Boom, you get a black hole. It's a natural process. It follows the laws of physics as we understand them. How would a white hole form? It would have to be the reverse of that process. Matter would have to spontaneously erupt from a singularity and form a star. That just doesn't happen. It's like expecting a scrambled egg to unscramble itself and go back into its shell. This is related to a fundamental law of the universe called the second law of thermodynamics. It basically says that things tend to get more disorderly over time. Entropy or disorder always increases. A star collapsing into a black hole is a process that increases disorder. A white hole forming would be a massive, impossible decrease in disorder. The universe just doesn't work that way. It doesn't run in reverse. So a white hole probably can't form now. But what if one was just there from the beginning? Maybe a white hole was created in the Big Bang along with everything else. This is a possibility. Physicists call these primordial white holes. They would have been born with the universe itself. If they existed, they would have been spewing out matter and energy ever since. They would be unstable, but maybe some small ones could have survived for a long time. Over billions of years, they would slowly leak their contents into the universe. When one finally died, it would let out a final, massive burst of energy. For a while, some astronomers thought this might explain a mystery called gamma ray bursts. These are the most powerful explosions we see in the universe. They are incredibly bright, short-lived flashes of gamma rays. For a moment, people wondered, could this be a primordial white hole exploding? The idea didn't last. We now have much better explanations for gamma ray bursts. We know they come from hypernovas, which are the deaths of extremely massive stars, or from two neutron stars colliding. The evidence for these other causes is very strong. We don't need white holes to explain them. And when we look out into the universe, we just don't see anything else that looks like a white hole. We don't see any points in space that are just endlessly gushing out new matter for no reason. So the formation problem is huge, but it gets worse. The second major problem is stability. Even if a white hole could somehow exist, it wouldn't last. The math that describes it is perfect and idealized. It assumes a universe that is completely empty except for the white hole itself. Our universe is not empty. It's full of stuff. There's dust, gas, and radiation everywhere. What happens if a single photon, a single particle of light, falls toward a white hole? Remember, space and time are rushing out of the white hole. As that photon gets closer and closer, it fights against this outward rush. This causes the photon's energy to increase dramatically. It gets blue shifted to an insane degree. Its energy would become nearly infinite as it approached the event horizon. This massive amount of energy would have its own gravity. And that gravity would be so strong that it would instantly cause the white hole to collapse. It would turn into a black hole. So, any white hole that might have existed would have been destroyed almost instantly. The moment the universe was created, radiation would have flooded everywhere. Any white hole would have immediately collapsed into a black hole. A white hole is like a unicorn. It's beautiful in theory, but it's too delicate to exist in the real world. This instability also destroys the idea of using the wormhole to travel between universes. The same math that shows the wormhole exists also shows that it's not traversable. The bridge connecting the black hole and the white hole pinches off and collapses faster than anything, even light, could travel through it. So if you jump into the black hole, you don't pop out of the white hole, you just hit the singularity and get crushed. So we have two massive problems. They can't form, and even if they did, they would be destroyed instantly. This is why most physicists do not believe that white holes are real. They think white holes are just a mathematical artifact. A ghost in the machine. The equations of general relativity are powerful, but they don't know everything. They don't include quantum mechanics, for example. Sometimes math gives you answers that are possible on paper, but don't happen in reality. For example, an equation for the motion of a ball might have two solutions, one for the ball moving forward in time and one for it moving backward. We know which one to pick for the real world. The white hole might just be the backward in time solution that we should ignore. Yes, but that's not quite the end of the story. The idea of a white hole is so strange that a few scientists have tried to find a place for it in more modern speculative theories. They've tried to see if there is any way to make a white hole real. One idea connects white holes to the Big Bang itself. The Big Bang was a moment when our entire universe erupted from a single, hot, dense point. That sounds a lot like the description of a white hole, doesn't it? A spontaneous explosion of matter and energy from a singularity. Some physicists have played with the idea that the Big Bang was a white hole. Perhaps our universe is the result of matter that fell into a black hole in some other older universe. This is a very speculative idea. It's hard to test, but it's an interesting way to think about where our universe came from. It suggests the cycle of universes, with black holes in one leading to white holes, or Big Bangs in another. Another idea tries to connect white holes to another deep mystery in physics, the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. If you burn a piece of paper, the information about what was written on it isn't gone forever. In theory, if you could collect every single particle of smoke, ash, and heat, you could reconstruct the original message. The information is just scrambled. But black holes seem to break this rule. If you throw a book into a black hole, the information in that book seems to be gone forever. It's trapped behind the event horizon. Then, Stephen Hawking showed that black holes are not completely black. They slowly leak radiation, now called Hawking radiation, and evaporate over incredibly long periods of time. But this radiation seems to be random. It doesn't contain the information about what fell in. So when the black hole completely evaporates, the information seems to be truly gone. This violates the laws of quantum mechanics. It's a huge problem. So, where does the information go? Some theories propose that it doesn't get destroyed instead, it gets stored and then comes out at the very end of the black hole's life. What if the black hole, after evaporating for trillions of years, doesn't just disappear? What if, in its final moment, it transforms into a white hole and releases all the information it ever swallowed? This is an idea from a field called loop quantum gravity, which is a competing theory to string theory. It tries to unite gravity and quantum mechanics. In this view, a singularity is not an infinitely dense point. Instead, quantum effects prevent a complete collapse. Matter gets squeezed down to an incredibly dense state, but not an infinite one. Then it rebounds. According to this idea, what we see as a black hole is actually something that is collapsing and then bouncing. The collapse takes a very long time from our perspective outside the black hole, but from the perspective of something falling in, it might bounce very quickly. This bounce would be the black hole turning into a white hole. So a black hole is a door in, and a white hole is a door out. But they are not separate things existing at the same time. They are the same thing at different points in its life. A black hole is the collapsing phase, and a white hole is the exploding, rebounding phase. This would solve the information paradox. The information doesn't get destroyed. It just gets held for a very, very long time and then released. This is still a highly speculative idea. It's on the very edge of theoretical physics. It's an attempt to fix the problems with the original white hole idea by adding quantum mechanics. It suggests that maybe small, primordial black holes created in the Big Bang have already evaporated and turned into white holes, releasing bursts of energy. Some physicists have even searched for radio signals that might be evidence of such events. So far, they haven't found anything conclusive. So, what is a white hole? On the one hand, it's a simple answer to a mathematical question. It's the time reversal of a black hole. It's a prediction of Einstein's theory of general relativity, a place where things can only come out and nothing can go in. It is a cosmic fountain, a source of matter and energy. On the other hand, it's almost certainly not real. At least, not in the simple way the original math described it. It violates other laws of physics, like the second law of thermodynamics. It seems impossible to form, and it would be so unstable that it would be destroyed the instant it came into existence. We have never seen any evidence for a white hole. We have looked. Our telescopes have scanned the skies for decades. We've seen black holes, we've seen neutron stars, we've seen colliding galaxies. We've seen the afterglow of the Big Bang, but we have never seen an object that just sits there, pouring matter and energy into space. So why do we even talk about them? We talk about them because they are a valuable tool for thinking. They show us the limits of our own theories. General relativity is a brilliant theory, but it's not complete. When it predicts something as strange as a white hole, it tells us that we are missing part of the picture. It tells us that our understanding of gravity, time, and the universe is not finished. The problems with white holes, the singularity, the instability, are signposts. They point to where our theories break down, and that is where new physics is waiting to be discovered. The paradoxes and impossible objects are what push science forward. They force us to look for better, more complete theories, like theories that include quantum gravity. The story of the white hole is a perfect example of how science works. An idea is born from mathematics. It's a beautiful, elegant, and symmetrical idea. Then, scientists test that idea against the messy reality of the universe. They ask hard questions. How does it form? Is it stable? What would it look like? Do we see any evidence for it? For the white hole, the answer to most of these questions seems to be no. The idea, in its purest form, doesn't seem to work. It's a failed prediction. But even failed predictions are useful. They teach us something. The white hole remains a fascinating what if. It's a ghost that haunts the equations of general relativity. It's a reminder that the universe described by our mathematics is not always the universe we live in. And it continues to inspire new, more creative ideas about the beginning of the universe, the end of black holes, and the fundamental nature of reality itself. It is a beautiful idea, the perfect opposite to the terrifying black hole. Not a bottomless pit, but an endless fountain. A source of creation. But for now, it seems to be just that, an idea, a mathematical echo of a black hole living only on paper, not in the stars.